What up, my quarantined homies? We're coming down to the come down, and I thought we'd have one more video from BC Calculus, uh, so I can see your beautiful faces. And if you're ever bored in the summer, you can always just watch this video on logistic growth. Um, and I'll try to make this one fast. You know how the other ones always take like an hour. This one's going to be like 15 minutes. I'm telling you, right? um, Logistic growth is a BC topic. Logistic growth is tucked into the chapter on differential equations. So we've done a lot with differential equations, um, but we haven't talked about BC. BC or logistic growth, we haven't talked about logistic growth. Logistic growth is a piece of exponential growth and decay. It's a certain type of exponential growth. Um, and so in the Barron's Guide, these notes are coming from the Barron's Guide. It actually talks about 3 different cases of exponential growth and decay. Okay, case 1 and case 2 you see in front of us. Case 1 and case 2 are A-B topics. So these are things we need to talk about as well, even though we have. Case 3 is logistic growth. So that's a couple pages down. So the first thing I wanted to mention is case 1. A positive quantity y increases or decreases at a rate that at time t is proportional to the amount present. I love this case 1. It says that the rate of change, dy dt, right, the derivative, is equal to Kentucky, okay? Woo boy, go Cats, right? So how do you solve this differential equation? We have done this before. You would move the y to the other side. You'd divide by y, and you'd multiply the dt to the other side, and you'd integrate, okay? So what you see here is the solution to case 1 on the next page. Okay, notice I divided by y, move the dt over, integrate both sides, and then you have to raise both sides as a power of e. So or you loop-de-loop it, so it's e to the kt plus c. Okay, and then there's a property of exponents that says I can split this plus sign in the power to a product with the same base. And e to the c power is the same thing as just having c. Because c is a constant that I don't know, e to the c power is still a constant that I don't know. And so what you have here in case 1 is y equals c e to the kt, okay? This case 1 is what is called the law of exponential growth and decay. If k is positive, then you have growth, as you see in the graph. If k is negative, then you'd have decay, because the reciprocal of e, 1 over e, makes, decay, okay? So if I bounce back up, page up, to here. What you see in the black on case 1 is the differential equation, and its solution is y equals ce to the kt. Okay, and this is the most basic kind of growth and decay that you have done from algebra 2 to even in pre-calculus. This is, a colony of bacteria growing on the water fountain, assuming that they have infinite amount of space to grow. So that's the catch with exponential growth, right? With the swoopy curve that goes up and up and up, you have to make sure there's enough room for it to go up and up and up. And that's why logistic growth is going to show up in a minute. Maybe rather than population of like people or wolves or elk or bacteria, think about money growing in a bank, continuously compounding interest, right? So this was our PERT formula. Right here, this CE to the KT was PE to the RT. It's PERT. So any differential equation of this kind, dy dt equals Kentucky, or dy dx equals Kentucky, it's a positive quantity proportional to the amount present, okay? It always has that solution. I'm not too concerned about case 1, case 2. We've solved case 2 equations before as well. Now case 2, you'll notice, has 2 parts to it. This is the rate of change is proportional not to the amount present like in case 1, but to a difference between that amount and a fixed constant. Okay, and there's 2 different ways this can happen. And it might be easier to like look at the next page real quick. But you notice in part A, the black differential equation is a positive k times a minus y, whereas the second one is a negative k times y minus a. So what does that switch do? And then the solutions are what's here in red. How do you get those solutions? You would integrate. How do you integrate? First, you have to separate the variables. So you would divide the a minus y to the other side on the first part, and you'd move the dt over and you integrate. And that would still require a log. And in this case, it'd be a u substitution. So there'd be a negative. Let's just show them, Marty. So if I jump down to the next page, go to the next page. So here are the solutions to both cases of case 2, both parts of case 2. So notice what ends up happening here is both of these solutions have a negative k exponent, okay? So what does that mean? That technically means that both of these solutions are exponential decay because it's k is a negative power. K is less than 0. Like if you look back over on case 1 over there, remember for k less than 0, the graph goes down. Well, for this first example on case 2, you'll notice the graph is increasing, but it's technically, you'll notice it's not increasing, it's concave down, right? It's not concave up and increasing like exponential growth. It's actually a decreasing curve, an exponential decay curve that's been flipped over. Because looking at the solution in red, the solution curve has a negative in front. So the negative flips the decay curve, flips it over, right? Happy face parabola comes sad face parabola. And so technically this is what is called negative decay. Okay, it's got a negative in front of the C, which means negative, and it's a negative in front of the K, which means decay. So it's negative decay. It's technically not growth. I know that's weird, but that's just what it is. And so this first example, you'll notice the graph is going up towards some like horizontal asymptote. It's like the graph is going up and up and up and reaching some sort of higher number, okay? Whereas the second part of case 2, the graph is going down and down and down towards some asymptote. It's almost basically just like if you look back over at case 1, you have c e to the negative k plus an a value, which just shifts the horizontal asymptote up. Okay, so the horizontal asymptote has been shifted up. So what like happens with this restricted growth? Like what makes this happen? What makes this happen are things like I got this here in the Barron's. Maybe I missed the page. Sorry. Um, Newton's law of heating says that a cold object warms up at a rate proportional to the difference between its temperature and that of its environment. So think about this first curve here, okay, in case 2. You have a cold piece of steak that you took out of your freezer and you put it on your counter, and it's going to warm up to room temperature, right? You take a popsicle and set it on your picnic table outside, and it's going to warm up and no longer be a popsicle, right? Um, that's Newton's law of heating. Just the opposite, Newton's law of cooling is the second example in case 2. If you have something that's warmer and you put it in the fridge, so after you eat dinner, you take your leftovers, you throw them in the fridge. What those leftovers are going to do is they're going to get colder and colder and colder, and they're going to reach some plateau, right? Some horizontal asymptote, which would be whatever temperature you keep your refrigerator at, right? If you put it in the freezer, it's going to reach an even lower temperature because freezers are set lower than refrigerators, right? Um, Other examples of restricted growth, because of air friction, the velocity of a falling object approaches a limiting value rather than increasing without bound. The acceleration is proportional to the difference between the limiting velocity and the object's velocity. I think this had something to do with one time I was at the drop zone ride at Kings Island. Okay, drop zone was the big tower that just goes like 300 feet in the air, and you're in a chair, right? And they raise you up and they just drop you, right? Um, Similar example is if you were to just drop a penny off of a high building, right? The penny doesn't like impale the guy's head and go through the ground, and go all the way down to hell, right? Well, I was on drop zone and these two kids were sitting next to me. I was like in high school, okay, maybe like early college, might have been 20, and these were like younger kids, and they had stacks of pennies. Okay, they had like 5 or 6 pennies stacked up, and we get up to the top and they put them on their knees, and then when the thing drops, the pennies obviously took a half a second later to drop than the people did. So the pennies actually floated in midair as we were going down this 300-foot drop. The pennies just went like, woo, like in front of us. You can't see me, but like I've got my hands up, and it's like the pennies literally like floated as we were floating down. It was cool. It was really cool. And then they just went ting 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 on the ground. Okay, so because of air friction, the velocity of a falling object approaches a limiting value rather than increasing without bound. The pennies didn't increase and increase and increase in speed. They reached a limiting value. So this is like real stuff. Another example they have in the Barron's Guide is if a tire has a small leak, the air pressure inside drops at a rate proportional to the difference between the inside pressure and the fixed outside pressure. So like people that are really smart that understand all this like physics and science and math, like this is like real talk, okay? So what you see here in black are the solutions to the differential equation and the answers are in red. So if I bounce back up, you may want to like pause it and you can write all these notes down before I go on because it's been like 5-6 minutes and I need to talk about logistic growth. So case one, the rate, the the quantity y increases or decreases at a rate proportional to the amount present. Case two, the quantity y increases or decreases at a rate that's not proportional to the amount present, but to a difference between that amount and a fixed constant. And the two examples there is either the amount's going to go up, which is the first part, part A, or the amount goes down, which is part B. So keep those two thoughts in mind. Okay, and there's the differential equations. Boom. Logistic growth. Logistic growth is both of them. Case one and case two, because what's 1 plus 2? Da-da! Case three, okay? Logistic growth is the rate of change of a quantity. So rate of change of a quantity is dy dt, or dy dx, or y prime, or f prime, right? The rate of change of a quantity may be proportional to both the amount of the quantity present and the difference between the fixed constant and its amount. Say what? So what we have here is the differential equation, and I'm trying to highlight it and you can't see because the cursor. Okay, I got my cursor now. Look, I'm boxing it in. Boxing it in. This is the differential equation. Notice dy dt equals Kentucky times a minus y. So this is case one where you have the rate of change is proportional to the amount present, and it's also proportional to the difference between that amount and a fixed constant a. That fixed constant a is the limiting value. Like that's the maximum that you're going to reach. So you notice this exponential curve at the first part of this thing, right? It's exponential growth. And then all of a sudden it flips and it becomes that negative growth. So instead of getting a J-shaped curve, we get an S-shaped curve, which is something I know Clements talks about in AP biology, or J curves and S curves. And so obviously what's going to happen if you have a water fountain with bacteria growing on it? They'll grow exponentially. Okay, at the beginning, the curve is exponential growth. You can see my little cursor there. But then at some point, it flips and changes to where it starts to like run, like the rate slows down. Okay. Notice the limiting value is the amount of space the bacteria have to grow. The limiting value is the amount of space that the wolves have to reproduce, as well as the food supply for the wolf can't run out, right? If the wolf runs out of food, then they're all going to die out. So there has to be some natural balance. And if you've ever seen The Matrix, one of the best movies ever, right? Mr. Anderson is being, oh, sorry, no, actually, it's Morpheus is being, kind of talked to by Agent Smith, and Agent Smith is humans are like a virus, and you think about what's going on right now with this crazy virus. But the issue is humans don't like plateau like a virus. They keep spreading out until they infect everything and they take over everywhere and like destroy their whole environment and everything that's around us. So anyway, that limiting value A, okay, is the highest the graph could ever get up to. Notice at half of A is where the logistic curve changes concavity. It's where the rate of rates changes. So from time zero up to a certain point, the graph is concave up. That means that the rate is increasing. The rate of change is increasing, right? It's the second derivative is positive. The rate of rates. If you think about the slopes of the tangent lines, and I could draw them on here. I just don't know where my cursor is anymore. This is an old Windows journal file and medium point. Now I can see it and it's red. So think about these tangent lines here that I'm drawing in. These tangent lines, they are getting steeper, right? What are the slopes of those tangent lines? The slopes of the tangent lines go from like 1 to 2 to 3. So the rate of the rate is increasing. And then at this point, A over 2, that is the point where the population or whatever is growing the fastest. Okay, that at that point of inflection, that's where the population or whatever the situation is growing fastest. And then the rate of rate slow down. Notice it's still increasing, right? The slope is still positive. This whole function has a positive slope. But what happens to the slope of the slopes? The slope of the slope, this first point is very steep, right? And then at this point, it's still pretty steep. At this point, it's not as steep, right? It's really hard to draw lines with the mouse and the little tracking pad. So at what point is the population growing the fastest? It's at a half of A. And notice A is going to be in your equation, going back to the black box, right? A is the number in the equation. Now, how do I solve this differential equation? It is a beast. And they would not ask you to do this on the AP exam. I can't imagine them ever doing this. Never done this before. They ask you to get this solution. So here is the solution. So what you need to know mostly is this is the differential equation in the black box. Kentucky times A minus Y. Its solution is A over 1 plus C e to the negative A kt power. And that A in the power is the same A that's in the numerator. C is a constant and K is a different constant. Okay. And so they usually have to give you some information to be able to find these things. Notice what happens here is, as you read these words in blue, as time goes to infinity, as t gets bigger and bigger and bigger, C e to the negative A kt power is going to go to 0. Okay. That's the whole, if you think about reciprocating the e into the base, the denominator, I'm sorry, then, the denominator grows faster and faster and faster. And so that term goes to 0. And what is 1 plus 0? Well, that's 1. So the denominator will go to 1. And what's A divided by 1? A. So as t goes to infinity, as the time moves on and on and on and on and on, the number of the population will be A. Okay, or what else? Is it just population? No. So in the Barron's Guide, they give some other pretty cool examples. So diseases spread through a finite population P at a rate proportional to the number of people, the number infected at time t, and the number of people not yet infected, which is people minus n, or in this case, A minus y, P minus n, A minus y. We can use different letters for all these things, right? So a disease spreads through a population P at a rate proportional to the number of people infected by time t and the number of people not yet infected. So that's the Kentucky part up here in the black box. This would represent the proportion of people that are already infected. A minus y is the number of people not infected. A would be the total number of people possible, right? The disease can infect more people than there are people, right? So you have the people infected and the people not infected. Another example, a rumor or fad or new religious cult. That would be the 713s. Often spread through a population P, according to the formula that you see there in red, okay? Where, Y is the number of people who have, sorry, I lost my reading. Y is the number of people who have heard the rumor, acquired the fad, or converted to the cult, and A minus Y is the number who have not. So a rumor or a fad or a disease, right? A third example is bacteria in a culture on a petri dish grow at a rate proportional to the product of the existing population and the difference between the maximum sustainable population and the existing population. Again, the maximum sustainable population is A. A is your like asymptote, horizontal asymptote, right? Your upper boundary, your limiting value, as they like to call it. So replace bacteria in a petri dish with fish in a small lake, ants confined to a small receptacle, fruit flies supplied with only a limited amount of food, yeast cells, and so on, right? So this logistic growth, it's like real talk. Advertisers sometimes assume that the sales of a particular product depend on the number of TV commercials for the product, and the rate of increase in sales is proportional to both the existing sales and to the additional sales conjectured as possible. So they conjecture, well, I think we can sell this much, the maximum. That's the A. So you have, the existing sales is Y, and back to the black box, right? The existing sales, and then you have A minus Y is the difference between the amount of sales possible and the existing sales. right? A minus y. Another one that I don't get because I'm not really sciencey. In an autocatalytic reaction, a substance changes into a new one at a rate proportional to the product of the amount of the new substance present and the amount of the original substance still unchanged. So that's definitely some crazy AP chemistry. Coach Thompson could go on for days about that, and I have no idea what it means. Um, so, uh, how do you go from the black differential equation to the red solution? I actually have it worked out. I solved it once, um, and never to do it again. And honestly, I don't even care if you write this down. I'm going to zip through it and then you can pause it and go back and write it down if you want to. But notice for logistic growth, just to mention the first step, how do you solve this differential equation? Is you first have to divide the y over and you have to divide a minus y over, and then you move the dt over, right? Because remember, y prime is like dy dt. I didn't write it as dy dt. I just wrote y prime to be lazy. So the first step is separating the variables. Always separate the variables. That's the first step. Now, how do you integrate this side? Notice it's not a simple natural log. This is a fraction whose denominator has factors. And when the denominator is factorable, that's when you must use partial fractions to split the one fraction into two smaller fractions. And I think because I had a minus y in our differential equation, I used m and q. Uh, for the numerators. Remember how I normally use A and B. So, so again, all this is here. And when you split it, M ends up being 1 over A, and Q ends up being 1 over A when you solve the differential equation, okay, or the partial fractions. So what that means is I have a common factor of 1 over A. So I have 1 over Y plus 1 over A minus Y, and this common factor of 1 over A, I just kind of leave out front, the 1 over A out front. So M and Q are the same thing. Now, what is the integral of 1 over y, or dy over y, is ln of y? What is the integral of dy over a minus y? This is kind of tricky. It would technically require u substitution. I didn't want to write out the steps for the u substitution because the rest of this is going to take forever anyway. And so it becomes a negative ln of a minus y. And that's because, remember, our variable is y. A is a constant. Y is the variable. What is the derivative of negative y? The derivative of negative y is negative 1. So when you do a u substitution, right, you get du equals negative, or du equals negative dy, and then you would divide the negative over, so negative du is dy. So the integral becomes the integral of du over u with a negative out front. And the integral of du over u is the ln of u, and u was a minus y with a negative out front. And that would equal the integral of k is kt plus the constant c, right? So as I scroll down through this, what I'm going to do now is use a property of exponents, right? There's a property of exponents that says, hey, when I'm subtracting, I can write it as a quotient, okay? Also, I have this 1 over a here. I can multiply 1 over a to the other side. So I get a times k times t. I also get a times c, but c is a constant that I don't know. So when I multiply by a, it's still just a constant I don't know. It's just c. Then I can get rid of the ln by doing the loop-de-loops, right? Or taking both sides as a power of e. And then I get 1 over a minus y equals e to the akt plus c. And this e to the c, remember, I can move this plus c and the exponent out front as a regular c. So there's my c e to the akt, okay? Now, how can I go about solving this equation for y? Because that's what you want to do, is you want to have it say y equals, right? I'm trying to solve dy dt for y equals. I'm trying to solve y prime for y, solving the differential equation for y. Well, notice this y divided by a minus y is a fraction, okay? What I can do is rewrite this fraction using long division, because the numerator is y, and I can divide the numerator by the denominator, negative y plus a. And negative y goes into y negative 1 times, and negative 1 times negative y plus a is y minus a. When you draw a line, change sign, make a rhyme, every time you get negative y plus a. So you end up with a over negative y plus a is like your remainder out of your divisor. Then I can take this negative 1 and add it to the other side, right? What I can then do is reciprocal the whole thing. Because if I have a over, like, if x over 2 equals 7, that means that 2 over x equals 1/7. You reciprocal the whole equation, basically cross multiplying and rewriting the bottom on top. And so when I do that, when I reciprocal, that puts my negative y on top. And then I can multiply the a to the other side. Okay, so the first part, how did I get rid of this +1 green? Or the -1 green as I added it to the other side, so the +1. So then I reciprocal both sides of this equation, and then I multiply a to the other side, right? When I multiply a to the other side, I get 1 over a. How about I just go to here? That's, oh, geez, this goes on forever. Okay, and then I got to subtract negative y plus a. I got to subtract the a over. So I subtract a over, and then I divide by a negative sign. So the negative a, when I subtract a over, becomes negative. When you divide it by a negative, it becomes positive. And then this fraction, the a over 1 plus e c to the akt power, gets a negative because I divide this negative in front of the y over. So I basically have it right here, y equals. But to show it as it is in the form on the other screen where it's in red, I need to get a common denominator with a and the fraction a over. So the common denominator means I got to multiply the first term a by 1 plus c e to the akt. And when I do that, I get a times 1, which is a. And then notice there's a minus a on top, so that cancels out. And then what do I got? I got an a times c e to the akt on top. Let me go down here so you can see that. Ace. We're almost done. There it is. So I got ace. This is just algebra. This is all algebra. Remember we did the integral a long time ago. The calculus happened a long time ago. So I have this numerator, and this is the common denominator from before. Well, you might notice, hey, there's something sort of common about this CE to the AKT power. So if I choose to take this factor and move it to the denominator with a -1 power, right? I can move it a whole thing down as a -1 power. Then I'm going to distribute it. So if I distribute CE to the AKT powers to the -1 times these two terms in this parentheses, obviously you get CE to the -KT to the -1. And then CE to the AKT times CE to the AKT -1 just makes +1. Still not finished. So then the last step is I can choose to rewrite the denominator with 1 plus. And notice what I do have here is I have c to a -1 power. But a number that I don't know to a -1 power is still a number that I don't know. So that's why it's just c. And then e to the AKT to the -1 becomes negative AKT. Holy mackerel. Maybe you skipped ahead in the video. You skipped that part. Now we're at the point where I can say, go ahead and skip through that part. If you want to write it down, go ahead. I would show that in class. Some people write it down, some don't, whatever. Some of you guys are never going to watch this anyway. But that's the solution. What's most important about this differential equation stuff or this logistic growth stuff is that this equation is the solution to this kya minus y differential equation. Okay. So that's the thing to know is if I have this problem, if I have this differential equation, I automatically know the solution is this one. You don't have to do all the stuff that I just did to prove it. Okay, I just proved this integral. Now I can just use it as a formula. And notice A, you're going to know A, and C and K, you have to have the information. So to look at an example of this, boom. In the Barron's Guide, they give one example, okay? And this is and I didn't write it down, so you'll have to listen. Oh well. Because of limited food and space, a squirrel population cannot exceed 1,000. It grows at a rate proportional both to the existing population and to the attainable additional population. If there were 100 squirrels 2 years ago, and 1 year ago the population was 400, how many squirrels are there now? Okay, so this is, kind of tricky, but notice what is actually happening. The problem is there's no calculus happening. There's no calculus at all. This is all algebra. Now, obviously, there's calculus inherent in this like differential equation. So going back to like the second sentence, the rate of the population of the squirrels grows proportional to both the existing population. So that's k times p. The existing population is p. The rate of change of population is dp dt. And to the attainable additional population. What is the attainable additional population? It said the first sentence was, because of limited food and space, the squirrel population cannot exceed 1,000. So A is 1,000. I know that right here, right now. A is 1,000. So I have Kp times 1,000 minus P. What does that solution to that differential equation look like? It looks like P, because I'm using P instead of Y. So its population equals, remember the numerator is A, over 1 plus CE to the negative a kt power. So I have this blue equation now, and I have two other colors that were given in the problem, red and green. You are told there were 100 squirrels 2 years ago. So if 2 years ago is times 0, right? The question is, how many squirrels are there now? Well, now is year 2. So I want to find P of 2, which you see over here in the end is black, P of 2. But what I have to do first is I have to find the variable C, or the constant C, and I have to find the constant K, the proportionality constant. So the first step is solve for C. How do you do that? Because it's always best to use 0 whenever you can. So take the blue equation and plug these red numbers into it. There's 1,000 on top, and it's 1 plus C is the number that I don't know. Now, if T is 0, what's 0 times K times negative 1,000? That's 0. What's E to the 0? That's 1. What's C times 1? That's C plus 1. So I have 1,000 divided by C plus 1. That's, so if you go over here to the red, 1,000 divided by 1 plus C, or C plus 1, is equal to 100, because that was the number of squirrels at time 0. Now I just cross multiply. C is 9. Cool. So what I have is, so far, my equation was blue, and now it's red. It's 1,000 over 1 plus 9 e to the negative 1,000 kt. So what else do they tell me? They tell me that a year ago, so 1 year after time 0, there were 400 squirrels. So this is now this green point, 1 comma 400. So I take my red equation, and I'm going to plug 400 in for the population P, and I'm going to plug 1 in for time. And this leaves me with a green equation that only has K as its unknown, right? K is the variable. And so what I'm going to do now is cross multiply. I'm going to solve for K. In order to solve for K, I get e to the negative 1,000 K power. So then I got to, like, loop-de-loop it. So it becomes, man, I went fast there, I guess. When I loop-de-loop it, it's ln of 1/6 divided by, what happened to my K? This is a problem that I worked out a long time ago. It ends up being a 1/6, I guess, is what happens. Oh, okay, that's what I did. I see now. Is e to the negative 1,000 K? I actually didn't solve for K. I never found out what K was. I just know that this number is 1/6. So I can just change this. So in blue, the e to the negative 1,000 K is 1/6. And then how many squirrels are there right now, which is 2 years after the beginning? So I just plug in 2. It turns out there's 800 squirrels. Okay, that's tough stuff. This is why it's BC calculus. It's tough stuff. And for you to do this over a video really sucks, and to not have a lot of practice. So I did try to make up a couple other practice problems. I'm slowly running out of time. I know you're like, geez, your videos last forever. Here's what's up. If you look in the bottom right corner, you'll see it's 12:23 p.m. So in 7 minutes, I'm going to have a Google Meet with 7th period. Whoop, whoop, whoop. Let me hear you, 7th period. 7th period's out there. Okay. So I'm going to finish these differential equations. Logistic growth differential equations in 7 minutes. Now it's 6 minutes because I got to meet 7th period at 12:30. Which of the following statements characterizes logistic growth population whose limiting value is L? Okay. The rate of growth increases at first. Okay. The rate of growth, remember, rate is slope. Increases is also slope. So what you're talking about is slope of slope. You're talking about derivative of derivative. Okay. The rate of growth increases, remember, means like if this is my slope, is like 1 out of 2, and then it's 2 out of 3, and then it's 3 out of 4, right? Those slopes are getting steeper. The slope of the slopes is increasing. So that is true. Remember, for logistic growth of a population, at first the rate of growth increases, and then what happens after some point is that the rate of growth decreases. The rate of growth decreases. So part 2, the growth rate attains a maximum when the population equals L over 2. Okay, the growth rate attains a maximum. And that is true. So going back to this graph that I just drew right there, that's pretty terrible. I'm gonna draw it again, right? Here's my logistic growth graph. It's the S curve, right? And when does this curve have its maximum slope? Which tangent line, So tangent line, tangent line, tangent line. Notice the tangent line is steepest at L over 2. L over 2 is when the growth rate attains a maximum. How do you find the maximum? Remember, you take the derivative of the function and set it equal to 0. So growth rate attains a maximum means you need to take the derivative of the rate. So it's the slope of the slope, right? Growth rate approaches 0 as the population approaches L. So as I get to the top of the curve, the growth rate gets smaller and smaller and smaller, right? Tangent lines at the top of the curve flatten out, right? See the tangent line, smaller and smaller and smaller. So that is also true. All three of these are true. Okay. I just thought I'd use these questions are from the Barron's Guide. I just thought I'd use these as like just to practice more about differential equations or about logistic growth and give you like the time to kind of think more about it, even though it's like I'm working them out for you. Which of the following is not logistic? Okay, so remember the logistic one, the note that we wrote earlier with dy dt equals Kentucky times a minus y. Well, it turns out there's a couple other ways you could write that. Okay, that was a ky. If you look at question part B looked a lot like that, right? There's a 0.01 for K and there's 100 for A. So this is definitely just logistic. Okay. Well, let's go back to part A. There's a P minus P squared. What can you do with P minus P squared is you can factor P times 1 minus P, which is like having 1P times 1 minus P, which is like having KY times A minus Y. So A is also good. Check. The same thing can be said on C. There's an X and an X squared. So I can out the X. I could also factor out some common factor. What is the common factor between 0.8 and 0.004? I don't know. Something. But still, even if I don't factor out the number, it's 0.8 minus 0.004x. And I'd want to factor out 0.004. But still, that is also the form of a logistic equation. Notice part D is 0.16. And what do you not notice next to the 0.16? Is the R. There has to be, it has to also be proportional to the amount present and the difference between that amount and the limiting value. So it's not D. Can't be D. F prime of t is k times f of t times a minus f of t. Well, that's just another way to write what I wrote up there in red up here. Okay. So not D, not logistic. I was hoping to get through. Oh well, we'll just do this last one, then I'll leave the rest for homework for you guys because I have 2 minutes to say hi to 7th period. 46. Suppose P denotes the size of an animal population, and its growth is described by the differential equation dp dt equals 0.002p times 1,000 minus p. The population is growing fastest initially when the population is 5,000, when p is equal to 1,000, when dp dt is 0. So when does the population grow the fastest? Again, we've talked about this now before. The population is growing the fastest, right? The curve is the steepest. When is this logistic curve steepest? Right here in the middle. And right there in the middle is when the population would be what? When the population is, well, going back to the equation, what's the maximum population you can have? Because that's the horizontal asymptote. The maximum is the 1,000, okay? From the equation, that's the A value. So it's not C, but it would be half of 1,000, or when the population is 500, okay? So like, I know there's no multiple choice questions on this year's AP exam, but maybe I'll use this video next year. What's up, class of 2021? I'll give you some more differential equations with logistic growth if you want, okay? And you can look at them if you want. Your AP exam is, 5 days away: Friday, Saturday, Sunday, Monday, Tuesday. Today is a Thursday. It is now 12:30, so I'm going to stop this video. Boom, boom. And I love you guys. Have fun with the rest of your life. Peace.